Something is fundamentally wrong with our understanding of comets. When astronomers captured 3I Atlas on their instruments, they expected to see the familiar patterns carved by decades of study. Jets that spiral and blur with rotation, tails that bow to solar wind, surfaces that respond predictably to sunlight. Instead, they found an object that refuses every rule in the book. Jets stretch over 1 million kilometers without bending. A body spins 43 times, while its features remain locked in place. The physics that govern every other comet in our records simply do not apply here. This is not about speculation or wild theories. This is about hard numbers that do not add up, observations that contradict established models, and a growing realization among researchers that 3I Atlas is forcing us to rewrite the fundamentals. What follows is the evidence, the physics, and the mystery that refuses to resolve itself. The image that broke the models. The frame arrived during a routine processing session at a major observatory, just another data set in the endless stream of celestial observations. But when the reduction pipeline finished its work and the image appeared on screen, the technicians stopped mid-analysis. What they saw should not exist according to any comet physics they knew. A cluster of bright streaks radiated from the central body of 3I Atlas, each one extending outward for distances exceeding 1 million kilometers. These were not the diffuse, curved plumes typical of cometary activity. They were razor-straight lines, sharp-edged and unbroken, maintaining their direction across vast stretches of space without the slightest curl or deviation. Multiple jets fanned outward at different angles, some climbing upward in the frame, others branching sideways, but every single one held its path with uncanny precision. The anti-tail appeared as a broad, faint streak pointing almost directly toward the sun, created by sunlight reflecting off dust particles suspended between Earth and the comet. This feature alone was unremarkable, a well-understood optical effect seen in many comets, but it served as a geometric anchor, confirming the sun's position relative to the frame and making the behavior of the other jets even more perplexing. While the anti-tail followed expected physics, those other streaks defied explanation. They emerged from the nucleus, an unresolved bright core at the center of the image, without showing any sign of the spiraling, smearing, or fanning that rotation should impose on material escaping from a spinning body. The field of view encompassed millions of kilometers, yet the jets maintained their orientation with a consistency that violated everything known about how comets behave. Standard models predict that jets tied to surface features should sweep around as the nucleus rotates, creating arced or spiral patterns in the expelled material. The rotation acts like a cosmic sprinkler, smearing each stream of gas and dust across a broad swath of space. But 3I Atlas showed none of this expected behavior. Each jet remained perfectly aligned, as if frozen in position despite the object's confirmed 16-hour rotation period. This was not an artist's interpretation or a computer simulation. It was a direct astronomical record captured with standard equipment and processed using well-tested reduction pipelines. The processing team ran through their calibration procedures multiple times, checking for instrumental artifacts or data corruption that might explain the unusual geometry. They found none. The image was clean, the features were real, and the implications were immediate and troubling. If these jets were genuinely tied to the spinning nucleus, the physics governing their formation had to be fundamentally different from anything observed in comets before. The team flagged the observation as an anomaly and sent copies to other research groups for independent verification. Within hours, confirmation came back from multiple observatories that had captured the same object during overlapping time windows. Everyone was seeing the same thing: straight, persistent jets on a body known to be rotating rapidly through space. The consistency across different instruments and observing sites ruled out local instrumental effects or processing errors. This was a real phenomenon, captured in multiple independent datasets, and it was about to upend decades of carefully constructed models about how comets work. The image became the focal point for a cascade of questions that would dominate discussions for months. How could jets maintain such perfect alignment while the object beneath them spun through dozens of complete rotations? What mechanism could suppress the natural smearing effect that should be unavoidable given the measured rotation rate and the time it takes for material to travel outward? And if the standard physics did not apply here, what did that mean for our understanding of not just this object, but potentially other interstellar visitors that might follow similar rules? The frame served as both evidence and challenge, a precise record of something that should not be possible, inviting researchers to either explain the impossible or admit that the rulebook needed fundamental revision, rotation measured to the minute. The photometric campaigns that tracked 3I, Atlas, through the summer months produced one of the most precisely measured rotation periods for any interstellar object on record. Multiple observatories coordinated their efforts, capturing thousands of brightness measurements as the comet moved across the sky. The data revealed a clear, repeating pattern. The object dimmed and brightened in a regular cycle, the signature of an irregular body tumbling through space as it reflected varying amounts of sunlight depending on which face pointed toward Earth. Sophisticated light curve analysis, drawing on established techniques used for asteroid characterization, extracted a rotation period of 16.16 hours. That is roughly 2/3 the length of an Earth day, a moderate to fast spin rate for a body several kilometers wide traveling at interstellar velocities. The precision of this measurement was exceptional. Multiple independent teams analyzed the same datasets and arrived at nearly identical results, with uncertainties measured in hundredths of an hour rather than the broader ranges typical of earlier comet observations. This was not an estimate or a rough approximation. It was a fixed, verified number backed by weeks of continuous monitoring and cross-checked against data from multiple instruments operating on different continents. The consistency across observing sites ruled out spurious signals from background stars, instrumental drift, or atmospheric effects that might create false periodicities in the data. The light curve's repeating pattern matched exactly what would be expected from a rotating body with an asymmetric shape reflecting sunlight as it spins. This rotation period became the critical reference point for every subsequent analysis of the object's behavior. If the nucleus completes one full rotation every 16.16 hours, then any feature anchored to the surface must sweep through 360 degrees in that time. A vent or fissure that starts out pointing in one direction will end up facing the opposite direction halfway through the cycle, then return to its original orientation when the rotation completes. Over the course of a day, any surface-based jet traces out not one, but 1.5 complete circles as the nucleus turns beneath it. The physics here is inescapable. The measured rotation rate locks down exactly how fast surface features change their orientation. And that rate in turn determines what patterns we should see in any material escaping from those features. The photometric campaign extended across multiple weeks, capturing the comet through different phases of its orbit and varying distances from the Sun. Researchers looked carefully for any signs of spin up or spin down, the gradual changes in rotation rate that can occur when outgassing creates torques on an irregular body. They found none. The period remained stable throughout the observation window, showing no detectable trend toward faster or slower rotation. This stability meant that any model attempting to explain the straight jets could not invoke a suddenly changing rotation rate or a nucleus that somehow locked itself into a non-rotating state. The object was spinning steadily and predictably at 16.16 hours per rotation, and it had been doing so for at least the entire duration of the monitoring campaign. The implications of this precise measurement became clear when combined with the jet observations. If jets are tied to specific locations on the rotating surface, and if the rotation period is known with such precision, then the expected appearance of those jets can be predicted with confidence. The math is straightforward. Material ejected at typical cometary speeds takes weeks to travel the distances seen in the images, during which time the nucleus completes dozens of full rotations. The result should be jets that spiral or arc dramatically across space, their paths smeared by the turning surface beneath them. But that is not what the images showed. Instead, the jets appeared straight and unwavering, as if the rotation period did not matter at all. This single discrepancy, the mismatch between what the rotation rate predicts and what the images actually show, became the foundation for everything that followed. It was a quantitative contradiction backed by solid measurements and verified across multiple independent datasets, and it demanded an explanation that no existing comet model could provide. Discovery at the observatory. Late in the observing session, the team working with fresh post-perihelion data encountered something that stopped their analysis workflow in its tracks. Images captured just days after 3I, Atlas rounded the Sun, revealed jets of dust and gas emerging from the nucleus with a geometric precision that seemed utterly at odds with the object's known rotation. Each jet traced a narrow, unwavering line across the frame, extending more than 1 million kilometers into space without showing any visible curvature, kink, or spiral signature that should result from a spinning body. The features were not subtle. They dominated the field of view, sharp enough to stand out even against the bright glow of the coma surrounding the nucleus. The processing team's first reaction was skepticism. Astronomical images are notorious for containing artifacts, glitches introduced by cosmic ray hits, tracking errors, or calibration problems in the data reduction pipeline. The team immediately began a systematic review, pulling up the raw files and running them through alternative processing chains to see if the straight-line jets were merely an illusion created by some flaw in their software. They checked the telescope's tracking logs, verified the flat field corrections, examined the background subtraction algorithms, and compared their results with images from other nights. Every test came back clean. The jets were real features, present in the raw data and confirmed across multiple independent exposures taken hours apart. The timing of this discovery amplified the puzzle. Only a few months earlier, coordinated photometric observations from several observatories had pinned down the rotation period at 16.16 hours, a result that had been cross-checked and confirmed to high precision. With that rotation rate, standard comet physics predicted that any persistent jet should have its path swept out into a broad arc as the nucleus turned beneath it. Material escaping from a fixed location on the surface would trace a spiral pattern in space, with the spiral's pitch determined by the ratio of the outflow speed to the rotational velocity of the surface. This was not controversial physics. It was basic geometry, confirmed in laboratory experiments, computer simulations, and observations of hundreds of comets in our own solar system. Yet the images from 3I, Atlas, showed no such spirals. The jets held their direction across weeks of observation and millions of kilometers of space. as if the nucleus were not rotating at all, or as if the jets were somehow decoupled from the surface rotation. The team prepared detailed notes documenting the anomaly, highlighting the discrepancy between the measured rotation period and the observed jet geometry. They included comparison images from well-studied comets showing the expected spiral patterns, making it clear that 3I Atlas was behaving in a fundamentally different way. These notes were circulated internally first, then shared with collaborators at other institutions who had access to independent datasets. The response was immediate and widespread. Research groups that had been tracking 3I Atlas through its perihelion passage pulled up their own images and confirmed the same features. Online collaboration platforms lit up with discussions as astronomers compared notes, posted annotated images, and debated possible explanations. Some researchers called for new theoretical work on jet confinement mechanisms that might keep the outflow collimated over such extreme distances. Others wondered whether the object's internal structure might be radically different from typical comets, with subsurface reservoirs or channels that could direct gas and dust along fixed paths regardless of surface rotation. Within the broader community, the phenomenon quickly earned the label of an anomaly, a term that carried weight in a field where most observations fit comfortably within established models. This was not just an unusual feature that required a minor adjustment to theory. It was a direct, quantitative contradiction between what the physics predicted and what the telescopes recorded. The jets were verified in multiple independent datasets, their straightness confirmed across different instruments and observing sites. The rotation period was solidly measured and showed no signs of the dramatic slowdown that might explain the lack of spiraling. The numbers did not add up, and no amount of data processing or alternative interpretation could make them fit into the standard framework. The discovery at the observatory forced the question: what kind of process, operating under what physical principles, could keep those jets so perfectly aligned while the object spun through dozens of complete cycles beneath them? The transit time problem. When a particle of dust breaks free from the surface of 3I Atlas, it carries with it a velocity typical of cometary outgassing, roughly 400 meters per second. This speed is not speculative. It is derived from spectroscopic measurements of gas expansion velocities and confirmed by models of how sublimating ice accelerates in trained dust particles. At this rate, the particle moves steadily outward through space, pushed by the pressure of the expanding gas and largely unaffected by the weak gravity of the small nucleus. The journey to the far end of the observed jets, those structures stretching more than 1 million kilometers from the core, is not instantaneous. It is a voyage that takes time, and that time becomes critical when trying to understand why the jets look the way they do. The arithmetic is direct. 1 million kilometers equals 1 billion meters. Traveling at 400 meters per second, a dust particle covers that distance in 2.5 million seconds. Convert that to more familiar units, and the result is just over 29 days. Every particle visible at the outer edge of a jet has been travelling for nearly a month since it left the nucleus. This transit time is not an abstract number. It is a clock running in the background of every image, determining how much time the nucleus has had to rotate while the material makes its outward journey. The nucleus itself, with its measured rotation period of 16.16 hours, completes a full 360-degree spin roughly every 2/3 of an Earth day. Over the course of 29 days, simple division gives the answer. The object completes approximately 43 full rotations. Every surface feature, every vent or crack or patch of exposed ice swings around 43 times, while the material it ejects crawls outward to the distances captured in the images. If a jet originates from a fixed spot on the surface, That spot points in every possible direction over the course of those rotations, sweeping through the full circle more than 40 times before the material reaches the edge of the visible structure. Standard comet physics predicts an unavoidable consequence of this geometry. As the nucleus rotates, any continuous jet tied to a surface feature should trace out a spiral or arc in space. The effect is analogous to water spraying from a rotating lawn sprinkler. The stream forms a curve, not a straight line, because the source is constantly changing direction. The spiral shape depends on the ratio of the outflow speed to the rotation rate. For 3I, Atlas, with 43 rotations occurring during the transit time, the expected result is a dramatic spiral pattern, with each arm of the spiral representing one complete rotation of the nucleus. Laboratory experiments have confirmed this prediction in controlled settings. Researchers spin ice samples in vacuum chambers, sublimate them under controlled heating, and watch as the resulting gas jets spiral outward in patterns that match theoretical predictions. Computer simulations do the same, modelling the dynamics of dust and gas escaping from rotating bodies and consistently producing spiral structures when the rotation period is comparable to or shorter than the transit time. These are not edge cases or special scenarios. They represent the expected behaviour under the conditions known to exist for 3I Atlas. Yet the images of 3I Atlas show no spirals. The jets remain straight, unwavering, and aligned across the full million-kilometre extent of their visible structure. The transit time calculation and the rotation period measurement leave no room for ambiguity. The numbers demand spiralling, the images show none. This is not a subtle discrepancy that might be explained by minor adjustments to the models, or by invoking unusual but plausible surface properties. It is a direct, quantitative break from fundamental expectations. A result that says either the jets are not tied to the rotating surface in the way every other comet's jets are, or the physics governing their formation is something entirely outside the current framework. The transit time problem sits at the heart of the anomaly. A simple calculation that produces a profound contradiction and forces every proposed explanation to confront the question, why do these jets refuse to spiral? Hypotheses under pressure. Faced with observations that defy standard models, researchers assembled a list of potential explanations, each one scrutinized against the available data. The first hypothesis considered was that the nucleus might have slowed its rotation so dramatically that jets would no longer smear into spirals. In typical comets, outgassing acts like a series of small thrusters, with jets creating torques that usually spin the nucleus up rather than down. The light curves from summer monitoring showed no evidence of a sudden drop in rotation rate. The 16.16-hour period remained stable across weeks of observation, with no trend toward longer periods that would indicate significant slowdown. The images themselves showed a body with active, vigorous outgassing, the opposite of what would be expected from an object that had somehow shed enough angular momentum to become nearly non-rotating. This hypothesis quickly fell into the unlikely category. The second model invoked sunlight-triggered jets, proposing that deep valleys or shadowed ice pockets on the surface might remain inactive until solar illumination hit at precisely the right angle. Each rotation would then trigger a brief pulse of outgassing as the feature faced the sun, potentially creating a series of discrete ejection events rather than a continuous stream. The mathematics of this scenario are straightforward. With jets travelling at 400 meters per second, material covers 1 million kilometers in about a month, during which the nucleus completes 43 rotations. If each rotation produces a single pulse, The jet should display 43 distinct clumps or knots of material, spaced roughly 23,000 kilometers apart along the jet's length. The images did not support this prediction. Instead of a string of separated features resembling pearls on a necklace, the jets appeared as continuous, smooth streams of material with no obvious periodic structure. High-resolution frames failed to reveal the expected spacing of emission events. While the sunlight triggering mechanism might explain some aspects of jets that faced directly toward the sun, it could not account for features extending in other directions or for the lack of visible pulsations in the observed structures. The model remained possible, but struggled to match the actual appearance of the jets. The fragment tail hypothesis occupied a more speculative position. This scenario suggested that the main nucleus might have broken apart near perihelion, with smaller pieces separating and forming their own straight tails as they vaporized. Each fragment would create its own tail pointing directly away from the sun, and the collection of these tails might resemble the multiple straight jets seen in the images. This explanation only worked if the nucleus had undergone a major disruption, splitting into several pieces that then moved apart while continuing to outgas. As of the most recent observations, no major observatory had released high-resolution images definitively confirming a breakup. The light curves remained consistent with a single, intact nucleus showing periodic brightness variations from rotation rather than the more complex patterns expected from a swarm of fragments. Spectroscopic data showed no evidence of multiple distinct emission sources that would be characteristic of widely separated fragments. Most researchers leaned toward the interpretation of an intact nucleus. Though without direct imaging at the highest possible resolution, the fragmentation scenario could not be completely ruled out. It remained on the list, but carried low probability based on the available evidence. The most controversial hypothesis suggested that the jets might function as controlled thrusters, analogous to the maneuvering systems on spacecraft. This idea remained at the bottom of the explanatory stack, invoked only if every natural model failed to account for the observations. Proponents of keeping this possibility in consideration argued that if the jets maintained their uncanny alignment despite all physical expectations to the contrary, then mechanisms outside the standard natural framework had to remain on the table, however unlikely. The probability assigned to this scenario was below 1%, but the insistence on transparency meant that even low probability explanations were documented and discussed openly rather than dismissed out of hand. Each hypothesis faced its own set of challenges when confronted with the data. The slow rotation model lacked observational support. The sunlight-triggered jet scenario predicted patterns not seen in the images. The fragment tail explanation was undermined by the apparent stability of the nucleus and the consistency of the light curves. The artificial mechanism hypothesis remained a last resort option, held in reserve but not actively pursued without further evidence. By the time the analysis reached this stage, the ranking was clear. Standard steady-state comet physics could not explain the observations. Exotic but natural models remained possible but unproven. The most speculative ideas were documented but not endorsed. Every hypothesis had to confront the same fundamental problem. The jets were straight, the rotation was measured, and the numbers did not fit. The pressure on existing models was not subtle, and the search for a viable explanation remained open, unresolved, and increasingly urgent. The retrograde trajectory. The orbital path of 3I, Atlas, stands out not just for its interstellar origin, but for its precise geometric relationship to the solar system's architecture. Standard orbital analysis reveals an inclination close to 180 degrees, meaning the object travels in a retrograde direction, moving backward relative to the planet's orbital motion. This retrograde orientation is not unusual by itself. Many comets from the Oort cloud follow retrograde paths. What makes 3I Atlas exceptional is how closely its trajectory aligns with the ecliptic plane, the flat disk defined by Earth's orbit around the Sun. The inclination deviates by less than 5 degrees from perfectly anti-aligned with the ecliptic, a configuration that is statistically rare among known interstellar objects. Neither Oumuamua nor Borisov, the two previously confirmed interstellar visitors, travelled such a precisely reversed course through the plane of the solar system. Oumuamua arrived at a steep angle to the ecliptic and departed the same way, passing through the system like a bullet fired from above or below. Borisov followed a more moderate path, but still showed significant inclination relative to the planetary plane. The combination of retrograde motion with near-ecliptic alignment makes 3I Atlas unusual in the small but growing catalogue of interstellar objects. This trajectory is not just a curiosity for dynamicists. It carries implications for how the object interacted with planetary gravitational fields during its passage, and for the timing of its discovery relative to Earth-based observing campaigns. Pre-perihelion observations established the size of the nucleus through measurements of reflected sunlight combined with assumptions about surface reflectivity. The results placed the object between 1 and 5 kilometers across, making it at least as large as Borisov and significantly larger than Oumuamua, which was estimated at only a few hundred meters in its longest dimension. This size difference matters because larger objects carry more mass and more kinetic energy, making their interactions with the solar environment potentially more dramatic and their behavior potentially more complex due to stronger internal thermal gradients and more substantial outgassing. The hyperbolic excess velocity, the speed the object possessed relative to the Sun when far from any planetary influence, clocked in above 23 kilometers per second. This figure sits at the upper end of the range observed for interstellar objects, indicating that 3I Atlas was moving fast relative to the local stellar neighborhood before it ever encountered our solar system. High excess velocity translates to high kinetic energy, meaning the object was carrying more momentum than either of its famous predecessors. This energy is relevant not just for trajectory calculations, but for understanding the forces at play during close solar approach, when thermal stress and outgassing rates peaked. Detailed trajectory reconstruction revealed another layer of oddity. The object's path brought it into close proximity with Mars, Venus, and Jupiter, while managing to stay out of optimal viewing geometry from Earth for months. Solar conjunction, the period when the object passed nearly behind the Sun from Earth's perspective, occurred just 8 days before perihelion. This timing kept the comet effectively invisible to most ground-based telescopes during the critical days when it was brightest and most active. Orbital modelers noted the improbability of a path that both grazed multiple planets and remained hidden from easy detection for an extended period. Trajectories are determined by the object's velocity and position when it enters the solar system, parameters set by its motion through interstellar space. The odds of those parameters conspiring to produce a path that samples multiple planetary environments while avoiding prolonged Earth visibility are low, though not impossible. The trajectory analysis raised questions about detection bias and the challenges of tracking fast-moving interstellar visitors. Objects on retrograde orbits spend less time within the solar system's inner regions compared to prograde visitors, and their high velocities mean they pass through optimal observing windows quickly. The combination of retrograde motion, near ecliptic alignment, and solar conjunction timing meant that 3I Atlas was always going to be difficult to study, regardless of its physical properties. This geometric challenge added an extra layer of difficulty to an already puzzling object, limiting the window for detailed observations and forcing researchers to make the most of brief opportunities when the comet was both bright enough and positioned favourably for telescopic work. Spectroscopic surprises. Spectroscopic analysis of 3I, Atlas, unveiled chemical signatures that deviated sharply from the norms established by decades of comet observations. The James Webb Space Telescope and the Very Large Telescope both targeted the object during its active phase, capturing high-resolution spectra of the gas plume surrounding the nucleus. The results revealed an abundance of nickel in the coma, with the nickel-to-iron ratio sitting orders of magnitude above what is typical for solar system comets. This was not a subtle enrichment. It was a dramatic chemical anomaly that immediately caught the attention of spectroscopists and planetary scientists. Nickel and iron are common elements in cosmic chemistry, found throughout the solar system in rocky bodies and metallic asteroids. In comets, these metals are typically present in trace amounts, locked into silicate dust grains or mixed with organic compounds. The ratio of nickel to iron in solar system comets generally reflects the solar abundance pattern, the baseline composition set by the cloud of gas and dust from which the Sun and planets formed. Deviations from this pattern occur, but they are usually modest and explainable by processes like preferential condensation of certain minerals or chemical fractionation during the comet's formation. The nickel to iron ratio, measured in 3I, Atlas, far exceeded these expected variations, presenting a composition more reminiscent of certain classes of metallic alloys than natural cometary material. The peer-reviewed analysis of the spectroscopic data described the odds of encountering such a ratio by chance, based on the current sample of known comets, as less than 1%. This statistical framing underscored the rarity of the observation and its significance for understanding the object's origin and composition. Engineered metal alloys designed for specific properties often exhibit non-solar elemental ratios, optimized for strength, corrosion resistance, or thermal characteristics. While no one was claiming the presence of manufactured material based solely on a nickel-to-iron ratio, the comparison to alloy compositions became a reference point in discussions about just how unusual the chemistry really was. Water, the defining component of most comets and the primary driver of their activity, was conspicuously scarce in the coma of 3I Atlas. Spectroscopic measurements from both the Very Large Telescope's ground-based instruments and the James Webb Space Telescope's infrared detectors confirmed that water vapor made up only about 4% of the coma's mass. This figure is strikingly low. Most comets derive the majority of their outgassing from water ice, sublimating as the nucleus heats up near the Sun. Water typically accounts for more than half of the volatile material released, with the remainder consisting of carbon monoxide, carbon dioxide, methane, ammonia, and various organic molecules. Even Borisov, the previous interstellar comet and an object already known for some chemical peculiarities, showed a much higher water content than 3I Atlas. The near absence of water in 3I Atlas raised immediate questions about what was driving the outgassing. If water was not the dominant volatile, what was? Carbon monoxide and carbon dioxide are common secondary components in comets, and both can sublimate at temperatures where water remains frozen, potentially explaining sustained activity even with low water content. But the spectroscopic data had to account for the full brightness and extent of the coma, and trace gases alone typically do not produce the vigorous outgassing observed in this object. The chemical composition painted a picture of a body that did not fit neatly into existing categories. The high nickel-to-iron ratio suggested either a formation environment very different from the one that produced solar system comets, or some process that concentrated nickel relative to iron after formation. The low water content indicated that the object's volatile inventory was dominated by species other than water ice, a composition more typical of certain classes of asteroids than of comets. Yet the object displayed clear cometary activity, with a bright coma and extended jets characteristic of sublimating volatiles. This combination of features, metallic chemical signatures with minimal water but vigorous outgassing, fell outside the expected range for both comets and asteroids, creating a compositional puzzle that paralleled the physical anomaly of the straight jets. Laboratory failures. Across research institutions worldwide, teams mobilized to recreate the conditions that might produce jets like those observed in 3I Atlas. At the Southwest Research Institute, engineers constructed a vacuum chamber setup designed to simulate cometary outgassing from a rotating nucleus. They prepared mixtures of water, ice, and dust, carefully chosen to match the properties of known cometary materials, and mounted these samples on a rotating platform inside the chamber. The rotation rate was set to match the 16-hour period measured for 3I Atlas, scaled down to laboratory dimensions. Heaters simulated solar illumination, driving sublimation from the ice surface, while cameras recorded the resulting jets of gas and dust. The jets erupted as expected, visible plumes streaming away from the rotating sample. But the plumes did not remain straight. They twisted, fanned out, and blurred as the surface rotated beneath them, tracing the spiral patterns predicted by standard physics. The researchers tried varying the mixture composition, adjusting the dust to ice ratio, changing the heating profile to mimic the sun's varying intensity at different distances, and introducing surface roughness to see if topography could affect the jet behavior. Every variation produced jets that curved with the rotation, never maintaining the unwavering alignment seen in the telescope images of 3I Atlas. Similar experiments at the CNRS laboratories in France and the Jet Propulsion Laboratory in California yielded identical results. Researchers introduced deep pits and shadowed valleys into their ice samples, testing whether topographic features might channel the outgassing in ways that resisted smearing. The pits did affect the jet directionality, sometimes producing more collimated streams than flat surfaces, but they could not prevent the jets from spiraling as the sample rotated. The jets pulsed with each rotation as the pits alternately faced toward and away from the heat source, but the pulses themselves still followed curved paths in space, not the straight lines demanded by the observations. The Max Planck Institute team took a different approach, focusing on computational simulations rather than physical experiments. They built detailed numerical models of gas and dust dynamics around rotating cometary nuclei, incorporating the latest understanding of sublimation physics, dust entrainment, and the interaction between gas flow and surface topography. The simulations allowed them to explore parameter spaces inaccessible to laboratory experiments, testing extreme outflow speeds, unusually rough surfaces, and highly irregular rotation states. The models consistently predicted that jets tied to surface features would curl with the nucleus's spin, producing spiral structures with shapes that varied depending on the parameters, but never disappeared entirely. The failure of these efforts to reproduce straight jets was not due to lack of sophistication or effort. The laboratories involved were among the most advanced facilities for studying cometary processes, staffed by researchers with decades of combined experience in planetary science. The experiments were carefully designed, the simulations rigorously tested, and the results were reproducible across different institutions and methodologies. The consistent outcome was clear. Under the conditions known to exist for 3I Atlas, jets should spiral. The fact that they did not point either to some critical physical ingredient missing from both the experiments and the simulations, or to a fundamental misunderstanding of how material escapes from this particular object. Some researchers floated the idea that magnetic fields might play a role in guiding the dust, keeping it aligned despite the rotation. Magnetic fields can indeed affect the motion of charged particles, and ionized gas in a comet's coma can create local magnetic structures. The FAST observatory team in China explored this hypothesis, but they found no evidence for the strong, organized magnetic fields that would be necessary to collimate jets over million-kilometer distances. Cometary magnetic fields are typically weak and chaotic, far too diffuse to exert the kind of control needed to explain the observations. As laboratory results continued to contradict the observed behavior, the focus shifted back to the data itself and to the possibility that the explanation lay not in refining existing models, but in identifying an entirely different physical mechanism. Internal communications from the observatories revealed a growing sense of urgency and frustration. The lack of a natural explanation was not just an intellectual puzzle, it was beginning to affect resource allocation, with telescope time committees prioritizing proposals related to the anomaly, while other projects lost access to observing time. The experiments had done their job by demonstrating what 3I Atlas was not. It was not behaving like any comet that could be recreated in a laboratory or simulated with existing physics. What it actually was remained the open question that no amount of vacuum chambers or computer models had yet answered: the water deficit. Water ice is the fundamental component that defines cometary activity in the solar system. When a comet approaches the Sun, increasing temperatures cause water ice on and just below the surface to sublimate directly into vapor without passing through a liquid phase. This process drives the most dramatic, visible changes in comets: the formation of a bright coma, the development of long tails, and the ejection of dust particles entrained in the expanding gas. Water vapor typically dominates the composition of cometary comae, often accounting for 50 to 90% of the gas released. This water-rich character is so consistent that it forms part of the working definition of what makes a comet, rather than some other class of small solar system body. The spectroscopic measurements of 3I Atlas revealed a starkly different composition. Water vapor made up only about 4% of the mass of the coma, placing it far below the range observed in even the most water-depleted solar system comets. This was not a moderate deviation that might be explained by variations in formation, location, or evolutionary history. It was a profound deficiency that demanded explanation. If water was not driving the outgassing, what was producing the bright coma and vigorous jets visible in every image of the object? Carbon monoxide emerged as a candidate. This molecule is common in comets and sublimates at much lower temperatures than water, allowing it to drive activity at greater distances from the Sun, where water ice remains frozen. Carbon dioxide is similarly volatile and often found in substantial quantities in cometary nuclei. Observations of other comets have shown that carbon monoxide or carbon dioxide-driven activity can produce significant comae even when water is scarce or absent. The spectroscopic data from 3I Atlas indicated elevated levels of carbon-bearing molecules consistent with these species playing a major role in the outgassing. But the sheer extent and brightness of the coma required more than trace amounts of volatile material. The observed activity level, the size of the hydrogen envelope detected by ultraviolet instruments, and the sustained ejection of dust over weeks of observation all pointed to a substantial reservoir of volatiles being released from the nucleus. If water was only a minor component, the other volatiles had to be present in large quantities and had to sublimate efficiently enough to match the observed outgassing rates. This compositional requirement placed constraints on what the nucleus could be made of and how it had formed. Water-poor compositions are not unknown in the solar system. Certain classes of asteroids contain little to no water ice, and some Kuiper Belt objects show evidence of surfaces dominated by methane, nitrogen, or carbon monoxide ices rather than water. But these objects typically do not display the vigorous cometary activity seen in 3I Atlas. The combination of low water content with high activity is unusual and suggests either an exotic volatile mix or a nucleus structure that allows efficient sublimation of non-water ices from a large surface area or subsurface. Reservoir. The water deficit also had implications for the object's thermal history. Water ice is relatively stable and can survive for billions of years in the cold environment of interstellar space or the outer solar system. More volatile ices, like carbon monoxide and methane, are less stable and can sublimate even at the extremely low temperatures of interstellar space if given enough time. An object travelling through the galaxy for millions of years might lose its most volatile components, leaving behind a more refractory composition. But 3I Atlas was actively outgassing these volatiles, suggesting that either it had not been travelling for an extreme duration, or it had some mechanism for retaining or producing these molecules despite prolonged exposure to interstellar conditions. The spectroscopic teams published detailed analyses attempting to reconcile the water deficit with the observed activity. They considered models where the nucleus was layered with a water-poor surface overlying a water-rich interior, but this scenario struggled to explain why water remained so scarce, even as outgassing intensified near perihelion. They explored the possibility of clathrates, cage-like ice structures that can trap other molecules and release them preferentially under certain conditions. But the spectroscopic signatures did not clearly support this interpretation. They examined whether dust properties might affect the observed gas-to-dust ratio, potentially making the coma appear brighter than the gas content alone would suggest. But the numbers still did not add up to match a typical comet. The low water content placed 3I Atlas in a chemical regime that straddled the boundary between comets and other small body populations. It behaved like a comet in terms of visible activity and dust production. It had the orbital characteristics of an interstellar intruder, but its composition was more reminiscent of certain types of asteroids or trans-Neptunian objects than of the icy bodies that populate the Oort cloud or come from other stellar systems as frozen remnants of planet formation. This compositional ambiguity fed into broader questions about what 3I Atlas actually was and where it might have come from, adding another dimension to the mystery that the straitjets had opened. The size uncertainty. Determining the size of a comet nucleus is never straightforward, especially when the object is surrounded by a bright coma that vastly outshines the solid core. For 3I Atlas, this challenge was amplified by the extreme distance from Earth and the limited resolution of available instruments during the critical observation windows. The most detailed attempt to measure the nucleus came from high-resolution imaging by spacecraft instruments operating near their maximum capability. But even these efforts ran into fundamental limitations imposed by physics and geometry. The Mars Reconnaissance Orbiter's HiRISE camera captured images of 3I Atlas from a distance of roughly 19 million miles. At that range, each pixel in the detector covered approximately 20 kilometers in the sky. The nucleus of 3I Atlas, estimated to be somewhere between 1 and 5 kilometers across, was smaller than a single pixel. What appeared in the images was not a resolved disk showing surface features or clear boundaries, but a single bright point surrounded by the diffuse glow of the coma. Estimating the size from such data required modelling, separating the light coming from the nucleus itself from the light scattered by dust in the coma, then using assumptions about surface reflectivity to convert brightness into physical dimensions. The official NASA estimates place the nucleus diameter between 1,400 feet and 3.5 miles. That range is vast, spanning more than a factor of 10 in size and more than 1,000-fold range in volume and mass. The width of this uncertainty reflects the difficulty of the measurement and the number of assumptions required to extract a size from unresolved data. If the nucleus has a high albedo, reflecting a large fraction of the incident sunlight, then it could be small and still produce the observed brightness. If the albedo is low, as is common for many cometary nuclei, then the object must be larger to account for the same brightness. Without direct measurement of the albedo or resolved imaging of the nucleus itself, both extremes remain possible. The brightness of the coma complicates the analysis further. The dust and gas surrounding the nucleus scatter sunlight far more effectively than the solid surface, creating a halo that can be thousands of times brighter than the core. Standard image processing techniques attempt to subtract this background using models of coma brightness profiles to isolate the contribution from the nucleus. But these models rely on assumptions about dust production rates, particle size distributions, and the geometry of the gas flow, all of which carry their own uncertainties. Small errors in these assumptions can translate into large errors in the derived nucleus size. Some independent researchers argued that the size might be even larger than the official estimates, particularly if the coma was unusually dense and efficiently scattered light. A denser coma would mean that more of the observed brightness came from dust rather than from the nucleus, requiring a larger nucleus to produce the observed dust mass. Conversely, if the dust was less efficient at scattering light than assumed, the nucleus could be smaller. The lack of resolved imagery left these competing interpretations in play, with no definitive way to choose between them based solely on the available data. Hubble Space Telescope observations provided another data point, but they faced similar limitations. Hubble's images from late summer showed a faint, grainy patch where 3I, Atlas, should be, but the nucleus remained unresolved. The technical summary from the Hubble team gave an upper limit on the diameter of about 5.6 kilometers, consistent with the high-rise estimates, but not adding substantial new precision. The James Webb Space Telescope's infrared observations suffered from the same problem. The nucleus was buried beneath the bright coma, and the wavelengths optimized for detecting cold, dust and gas did not penetrate to reveal the solid core. The size uncertainty mattered for more than just academic cataloguing. The mass of the nucleus, which scales with the cube of the radius, determines the object's gravitational field and its resistance to tidal forces, spin-up from outgassing torques, and potential fragmentation. A 1-kilometer nucleus has very different structural properties than a 5-kilometer nucleus, and the forces acting on it during a close solar approach would produce different outcomes. Without a firm handle on the size, models attempting to explain the object's behavior had to accommodate a wide range of possible nucleus masses, each with its own set of physical implications. The persistent inability to resolve the nucleus or pin down its size with confidence added to the sense that 3I Atlas was slipping through the observational net. Billions of dollars in space-based assets had been pointed at the object, yet the most basic physical parameter, how big it was, remained frustratingly uncertain. The unresolved nucleus became a symbol of the broader challenge facing researchers. An object that refused to yield its secrets even to the most advanced instruments humanity had deployed. the hydrogen envelope. MAVEN's ultraviolet spectrograph revealed one of the most expansive structures associated with 3I Atlas, a finding that shifted attention from visible features to the invisible processes shaping the object's interaction with the solar environment. Operating from its orbit around Mars, the spacecraft used its imaging ultraviolet spectrograph to map the distribution of neutral hydrogen around the comet. The observations detected Lyman alpha emission, ultraviolet light produced when hydrogen atoms are excited by solar radiation and then re-emit photons at a characteristic wavelength. The resulting data showed a hydrogen envelope stretching nearly 33,000 miles across, far larger than any structure visible in optical images. This envelope was not a solid or even a dense structure. It consisted of individual hydrogen atoms moving away from the nucleus at speeds determined by the temperature of the gas and the interactions with sunlight. The atoms originated as water molecules or other hydrogen-bearing compounds released from the nucleus, then were broken apart by solar ultraviolet radiation through a process called photodissociation. Once freed, the hydrogen atoms continued to move outward, forming an extended cloud that marked the comet's presence across a region of space dwarfing the nucleus itself. The size of the hydrogen envelope provided direct information about the rate at which hydrogen-bearing molecules were being released from the nucleus. Larger envelopes indicated higher production rates, assuming similar solar conditions and distances. The MAVEN team's analysis accounted for variations in solar activity and the comet's changing distance from the Sun throughout the observation period, using established models of how solar radiation affects hydrogen clouds in space. Their calculations suggested that the production rate was substantial, consistent with vigorous outgassing, even though water vapor was a minor component of the coma. This implied that other hydrogen-bearing molecules, possibly organic compounds or hydrogen gas itself, were contributing to the total hydrogen budget. The envelope's existence also indicated that ionization processes were active in the coma. Hydrogen atoms do not remain neutral indefinitely when exposed to the solar wind and solar ultraviolet radiation. Photoionization strips electrons from the atoms, converting them into protons and creating a population of ionized hydrogen mixed with the neutral cloud. The solar wind, a stream of charged particles flowing outward from the Sun, also interacts with the neutral gas through charge exchange reactions, where solar wind protons steal electrons from cometary hydrogen atoms. Both processes convert neutral material into plasma, creating an environment where electric and magnetic fields become important players in determining how material moves and how the comet appears. The MAVEN observations captured snapshots of this dynamic system at multiple points during the comet's passage, allowing researchers to track changes in the hydrogen envelope as solar conditions varied. The size and brightness of the envelope fluctuated in response to changes in solar wind pressure and ultraviolet flux, demonstrating that the structure was not static but continuously responsive to external forcing. This variability was expected based on observations of solar system comets, but seeing it play out in an interstellar visitor confirmed that the basic physics of comet solar wind interactions applied to 3I Atlas, despite its unusual properties. For plasma physicists, the hydrogen envelope and the ionization processes it revealed represented the main scientific value of 3I Atlas. The object was not just a curiosity because of its straight jets or its interstellar origin. It was a natural laboratory for studying how cometary material interacts with the solar wind, how magnetic fields are draped around active nuclei, and how plasma instabilities develop in the boundary region between the neutral coma and the ionized solar wind. These processes are fundamental to understanding not just comets, but also the interaction between any planetary atmosphere and the stellar wind from its host star, with applications ranging from Mars's atmospheric loss to the habitability of exoplanets. The MAVEN team published their findings with detailed descriptions of the observation geometry, the data reduction techniques, and the modeling assumptions used to convert brightness measurements into hydrogen production rates. They emphasized that the envelope's large size and the evidence for substantial ionization meant that 3I, Atlas, was surrounded by a complex plasma environment, one where electromagnetic forces were as significant as gravity or gas pressure in shaping the flow of material. This plasma environment would become even more important when a solar eruption headed toward the comet, setting up a natural experiment that observers hoped would reveal even more about how interstellar visitors respond to the sun's most violent outbursts. Anticipating the impact. Solar observatories detected the coronal mass ejection as it erupted from the sun's surface, a massive burst of plasma and magnetic field accelerating outward into interplanetary space. These eruptions are among the most powerful events in the solar system, capable of disrupting satellite operations, triggering auroras on Earth, and fundamentally altering the space environment around any object in their path. The CME headed toward 3I Atlas was well observed, with multiple spacecraft tracking its evolution and speed as it propagated away from the Sun. Heliophysics teams ran predictive models to calculate when the CME would reach the comet's location. The models incorporated measurements of the CME's velocity, approximately 1,000 kilometers per second, and the three-dimensional geometry of its expansion. The predictions converged on a specific time window. The CME's leading edge would arrive at 3I, Atlas, around midday universal time. This precision was possible because the CME's trajectory and speed were well constrained by observations from multiple vantage points, including spacecraft positioned at different locations in the inner solar system that provided stereoscopic views of the eruption. The anticipated impact generated significant interest across the solar physics and cometary science communities. Tail disconnection events had been observed in solar system comets, dramatic occurrences where the plasma tail is severed from the nucleus by the shock front of a CME. The disconnected tail drifts away into space while the comet grows a new tail from fresh material, creating a striking visual signature that has been captured in images of several well-studied comets. But no one had ever observed such an event in an interstellar object, and the opportunity to see how 3I, Atlas, would respond was scientifically valuable. Researchers coordinated their observations with ground-based telescopes, space-based imagers, and plasma instruments, all preparing to record data before, during, and after the predicted arrival time. The MAVEN team programmed their ultraviolet spectrograph to take frequent measurements of the hydrogen envelope, looking for sudden changes in brightness or extent that would signal a major disturbance. The PUNCH satellites, designed to image the inner heliosphere, were tasked with monitoring the comet's tail for any signs of disconnection or disruption. Ground-based observers planned imaging campaigns to capture visible light changes in the coma and tail structure. The physics of a CME impact on a comet is complex. The CME carries its own magnetic field embedded in the plasma, and this field interacts with the magnetic field draped around the comet by the solar wind. When the two magnetic structures collide, they can reconnect, releasing energy and accelerating particles. The shock front at the leading edge of the CME compresses the plasma ahead of it, creating a jump in density, temperature, and magnetic field strength. This compressed region can sweep away the comet's plasma tail, severing the connection between the ionized gas and the nucleus. For 3I, Atlas, with its extensive hydrogen envelope and evidence of substantial ionization, the impact promised to be particularly dramatic. The large spatial scale of the plasma environment meant that the CME would interact with cometary material over a vast region, potentially creating observable effects across hundreds of thousands of kilometers. The presence of significant plasma in the coma also meant that any tail disconnection event would be visible in both optical images, which show dust and ionized gas, and in ultraviolet observations, which track the neutral hydrogen and the ionization state of the coma. In the hours leading up to the predicted impact time, data streams from the various instruments were monitored in near real time by teams spread across multiple continents. The tension was not about danger. Comets and CMEs interact regularly, and this event posed no threat to Earth or spacecraft, but about the scientific opportunity. If the impact occurred as predicted and the observations captured the details, the data would provide unique insights into plasma physics under conditions impossible to replicate in any laboratory. If the impact was less dramatic than expected, or if clouds or instrumental problems interfered with the observations, the opportunity would be lost. The countdown to impact became a focal point for researchers invested in understanding 3I, Atlas. For a brief window, the object was not just an astronomical puzzle or a curiosity from another star system. It was a target for a controlled experiment, albeit one controlled by the Sun rather than human design, that promised to reveal how the dynamic solar environment shaped the behavior and appearance of this enigmatic visitor. Conflicting tail observations, the wide-field cameras aboard NASA's Punch mission captured 3I, Atlas, as a small, faint object trailing what appeared to be a short, stubby tail. The images, taken in late September and early October, showed a tail structure that seemed almost truncated, lacking the long, sweeping appearance typical of bright comets. This abbreviated tail immediately sparked questions about whether something unusual was happening in the comet's plasma environment. Was the tail being disrupted by solar wind conditions? Has recent outgassing patterns changed, or was this simply a projection effect, with the tail pointing nearly toward or away from the observer and thus appearing shorter than it actually was? Closer examination of the Punch data revealed that the apparent stubbiness might be as much an artifact of the instrument and processing as a real physical feature. Punch was designed to study the solar wind and faint coronal structures extending from the Sun, not to capture fine detail in cometary tails. Its detectors were optimized for broad, diffuse features, and the image stacking routines used to improve signal-to-noise tended to blur or suppress extended low-contrast structures. When faint tail material was spread across many pixels, the processing algorithms sometimes failed to distinguish it from background noise, effectively erasing parts of the tail from the final images. This meant that what looked like a short tail in Punch images might actually be a longer structure with its outer portions lost in the data reduction process. The Lucy spacecraft, operating much farther from 3I, Atlas, and observing from a completely different angle, recorded something even more perplexing. On September 16th, Lucy's cameras captured a faint streak extending from the comet's position, but this streak pointed toward the Sun rather than away from it. Comet tails are supposed to point away from the Sun, driven by solar radiation pressure and the solar wind pushing material in the anti-solar direction. A sunward-pointing feature violated this basic expectation and demanded explanation. The Lucy team proposed several possible interpretations. Projection effects could create the illusion of a sunward tail if the actual tail was oriented at a steep angle to the line of sight, and the perspective from Lucy's distant vantage point compressed the three-dimensional structure into a misleading two-dimensional appearance. Forward scattered dust, particles moving ahead of the nucleus along its orbital path, could also produce a feature pointing in an unexpected direction if the scattering geometry was just right. A transient jet angled forward could create a temporary streak that might be misinterpreted as a tail in a single snapshot, without time-resolved observations to track its evolution. The challenge was that other spacecraft and ground-based observations from the same time period showed a classic anti-solar tail, the expected dust tail pointing away from the Sun as radiation pressure pushed particles outward. The punch images, despite their limitations, showed a tail in the general anti-solar direction. Ground-based observers reported tails extending in the direction consistent with solar wind pressure. Only Lucy's data showed the anomalous sunward feature, suggesting that the observation was specific to Lucy's unique viewing geometry, rather than indicative of unusual comet behavior. Online astronomy forums and preprint discussion boards filled with speculation about the conflicting tail observations. Some commenters suggested that 3I Atlas might have multiple tail structures pointing in different directions, a phenomenon observed in a few solar system comets where distinct dust and plasma tails separate due to their different responses to solar forcing. Others argued that the discrepancies simply highlighted the difficulty of imaging a faint, fast-moving object from multiple widely separated vantage points, each with its own instrumental limitations and processing artifacts. NASA's official communications leaned toward caution, emphasizing that single instrument anomalies should be interpreted carefully and that the broader pattern across multiple observations showed conventional tail behavior. The message was clear. Don't overinterpret outliers when the majority of the data shows expected features. Yet the presence of these conflicting observations added to the overall sense that 3I Atlas was a difficult target, one that seemed to produce different appearances depending on how and when it was observed. Whether this variability reflected real physical changes in the comet, the limitations of the instruments used to study it, or the quirks of viewing geometry remained an open question, contributing to the difficulty of assembling a coherent picture of what 3I Atlas actually looked like and how its tails were behaving during its most active phase. Amateur triumphs. While flagship space missions struggled to deliver clear images of 3I Atlas's nucleus and jets, a different community was achieving remarkable success using far more modest equipment. Amateur astronomers, operating from backyard observatories and small private facilities, began posting images of the comet that revealed details invisible in the official releases. These images, captured with telescopes costing a fraction of what space agencies spend on individual instruments, showed the comet's structure with a clarity that stunned professional researchers and sparked widespread discussion about the accessibility of cutting-edge astronomical observations. The equipment used by these amateurs was sophisticated but not exotic. Telescopes with apertures between 10 and 20 inches, cooled CCD or CMOS cameras capable of long exposures with low noise, and carefully calibrated optical systems allowed dedicated observers to integrate light over many hours, building up signal from the faint comet against the background sky. Processing software, much of it freely available or affordable to hobbyists, enabled image stacking, alignment, and enhancement techniques that brought out subtle features buried in the raw data. The total cost for a complete setup ranged from $5,000 to $30,000, accessible to serious amateurs but representing less than a 10,000th of the cost of a space mission. Between November 8th and November 19th, a steady stream of high-quality amateur images appeared on astronomy forums, social media platforms, and image-sharing sites dedicated to astrophotography. The consistency across these independent observations was striking. Night after night, observers from Spain, Arizona, Australia, and Japan recorded the same structures. A bright, well-defined coma surrounding the nucleus, a clear anti-sunward tail extending across the frame, and 4 to 5 distinct jets radiating from the core region. The jets showed up as narrow, bright features against the fainter background of the coma, with their orientations and relative brightness changing from night to night as the nucleus rotated. The time series nature of these observations proved particularly valuable. With a rotation period of about 16 hours, the comet's appearance changed significantly over the course of a single night's observing session. Amateurs who imaged the comet multiple times per night, or who coordinated with observers in different time zones to provide continuous coverage, were able to track how the jets shifted in position and intensity. This data confirmed predictions from the light curve analysis about the nucleus's spin state and provided direct visual evidence of rotational modulation in the jet activity. The jets were not static features. They brightened and faded, appeared and disappeared, as different regions of the nucleus rotated into and out of sunlight. The collaborative nature of the amateur effort amplified its impact. Observers shared their images in online forums, discussed processing techniques, and coordinated observation times to fill gaps in coverage. Some amateurs with expertise in photometry measured brightness variations and contributed light curve data points that complemented professional observations. Others focused on color imaging, using filters to capture the comet at different wavelengths and reveal information about the dust and gas composition. The community functioned as a distributed observatory, with dozens of independent instruments providing continuous monitoring that no single professional facility could match. On November 16th, one image in particular went viral across both amateur and professional networks. A high-resolution frame captured with a 16-inch astrograph and a high-end camera showed the comet's jets arcing gracefully across a field of distant galaxies visible in the background. The contrast between the sharp cometary features and the faint background galaxies emphasized both the quality of the image and the dynamic nature of the foreground object. The image was reposted hundreds of times, featured in news articles about the comet, and cited by professional astronomers in presentations and papers. The equipment used to capture it cost approximately $24,000, a sum that stood in stark contrast to the billion-dollar investments behind NASA's spacecraft, but had delivered a more useful scientific product for understanding the comet's jet structure. The success of the amateur campaign raised pointed questions about resource allocation and observational priorities in professional astronomy. If backyard observers with modest budgets could reveal the comet's detailed structure more effectively than space-based platforms, what did that say about the design priorities of those platforms, or about the processing and release policies governing their data? The answer was not that space missions were worthless, or that professional astronomy had been surpassed by amateurs. Space-based instruments provided unique capabilities, access to wavelengths blocked by Earth's atmosphere, vantage points impossible from the ground, and long-term monitoring unaffected by weather or day-night cycles. But for this particular object, at this particular time, the combination of the comet's brightness, its location in the sky, and the specific observational requirements for capturing jet structure favored ground-based imaging with modest apertures and long integration times. The amateurs had the right tools for the job and the motivation to use them night after night, producing a dataset that became indispensable for researchers trying to understand how 3I, Atlas's jets, behaved. Their contribution was not just a feel-good story about citizen science. It was a genuine advance in the observational record, providing data that shaped professional interpretations and challenged assumptions about what equipment was necessary to do frontier astronomical research: the plasma dominance. The label Comet comes with expectations rooted in decades of observations of solar system objects. Comets are defined by their icy composition, their development of comet and tails as they approach the Sun, and their behavior under solar heating. But labels can be limiting, especially when an object displays properties that stretch or break the boundaries of established categories. For 3I, Atlas, the Comet label was applied early and reinforced in official communications, but the actual data told a more complex story that resisted simple classification. The MAVEN ultraviolet observations revealed a hydrogen envelope 33,000 miles across, a structure dominated by plasma processes. The envelope's size and the evidence for extensive ionization meant that electromagnetic forces, electric and magnetic fields generated by the interaction between the solar wind and cometary material, played major roles in shaping what observers saw. This was not just an icy body sublimating passively under solar heating. It was an active plasma system, with the coma swelling and contracting in response to solar wind pressure, magnetic fields threading through the ionized gas, and complex interactions between neutral atoms, ions, and electrons determining the flow of material away from the nucleus. Plasma physics offers explanations for phenomena that do not fit neatly into traditional comet models. Electric fields can accelerate charged particles to high speeds, creating narrow, collimated beams of material that might appear as straight jets even on a rotating body. Magnetic field lines, if organized in particular configurations, can channel plasma flows along specific directions, maintaining jet alignment across large distances. Double layers, regions where electric potential changes rapidly, can form boundaries between different plasma regions and affect how material moves through the coma. None of these processes are typically included in standard comet models, which focus on gas dynamics, dust entrainment, and solar radiation pressure. The extreme chemical composition of 3I, Atlas, added to the case for plasma-dominated behavior. The high nickel-to-iron ratio and the near absence of water suggested a material composition unlike typical solar system comets. Some researchers pointed out that metals in a plasma environment behave very differently than in neutral gas. Metallic ions can interact strongly with magnetic fields, and if the nucleus was releasing substantial amounts of metal vapor, the resulting plasma might develop electromagnetic structures not seen around water-rich comets. This remained speculative, but it opened avenues for thinking about the object in ways that did not rely on conventional comet chemistry. A small number of theorists explored even more speculative ideas, including the possibility of plasma bions, self-organized structures that can form in dusty plasmas under certain conditions. Plasma bions are not well understood and remain controversial within the plasma physics community, with most researchers skeptical that they could exist at the scales and densities relevant to cometary environments. But the concept illustrated a broader point. Plasma can organize itself in complex ways, forming structures and patterns that are not immediately predictable from simple gas dynamics. If 3I, Atlas's environment, was truly plasma-dominated, then models developed for neutral gas-dominated comets might simply not apply. The resistance to considering plasma-focused explanations came partly from the weight of tradition. Cometary science has been built on decades of successful modelling using gas dynamics, radiative transfer, and dust mechanics. These tools have explained the behaviour of hundreds of comets, and there is a natural reluctance to abandon or significantly modify frameworks that have proven so successful. But 3I, Atlas, was not behaving like those hundreds of other comets. Its straight jets, its unusual composition, its extensive ionized envelope, all pointed toward an object where the plasma physics might be the story, not just a minor correction to gas dynamical models. The question was not whether 3I Atlas was a comet or something else in some binary sense. It was about what framework was most useful for understanding its behavior. If calling it a comet meant importing assumptions about water-rich composition and gas dynamic dominated outgassing, then the label was misleading. If it meant simply acknowledging that the object developed a coma and tail near the Sun, then the label was accurate but not very informative. The real challenge was to build models that captured the plasma-dominated character of the environment while still accounting for the solid nucleus, the dust production, and the observable features that place the object in the realm of small body science rather than purely heliophysics. This middle ground, where cometry and plasma physics intersected, was less well explored than either field alone. Few researchers had expertise spanning both domains, and the tools and techniques used in each community were often unfamiliar to the other. Bridging that gap required collaboration and a willingness to question assumptions on both sides. For 3I Atlas, that bridging effort was still in its early stages, with most analyses favouring one framework or the other rather than attempting a true synthesis. The plasma dominance of the environment was clear from the data, but translating that dominance into a comprehensive model that explained the straight jets, the chemical anomalies, and the object's overall behaviour remained an unsolved problem. Unresolved questions. The data accumulated over months of observation left researchers with a detailed record of 3I Atlas's behaviour, but without a satisfying explanation for its most striking features. The straight jets remained the central puzzle. Every attempt to reproduce them in laboratories failed. Every simulation predicted spiralling that was not observed. The transit time calculations and rotation period measurements left no room for ambiguity. The physics demanded smeared, curved jets, yet the images showed none. This was not a small discrepancy that could be waved away with minor adjustments to models. It was a fundamental mismatch between theory and observation. The chemical composition added layers to the mystery. The high nickel-to-iron ratio defied expectations for natural cometry material, pointing toward either a very unusual formation environment or processes that concentrated metals in ways not seen in solar system comets. The water deficit meant that standard water-driven outgassing models could not explain the vigorous activity, forcing consideration of alternative volatile sources and potentially exotic nucleus compositions. Combined with the plasma-dominated environment revealed by Maven's hydrogen envelope observations, the chemistry suggested an object that might require entirely new categories to describe accurately. The size uncertainty persisted despite observations from multiple advanced instruments. Without resolved imaging of the nucleus, models attempting to explain the object's behavior had to accommodate a factor of 10 range in size, each value implying different physical conditions and structural properties. The inability to pin down this most basic parameter limited the precision of any theoretical work and left open the possibility that the nucleus might be fundamentally different in structure than assumed, perhaps porous or fragmented in ways that affected how it responded to solar heating. The tail observations from different platforms showed inconsistencies that were never fully resolved. Whether these represented real variability in the tail structure, artifacts of different instrumental capabilities and processing methods, or effects of viewing geometry remained unclear. The ambiguity highlighted how difficult it was to piece together a coherent picture of the object from observations taken by instruments optimized for different purposes and operating under varying constraints. The failure of natural models to explain the observations did not automatically validate exotic or artificial hypotheses. The absence of a conventional explanation was not evidence for an unconventional one, but it did mean that researchers were left without a satisfactory answer to the fundamental question. What physical process allowed 3I Atlas to maintain straight jets over million-kilometre distances despite rotating dozens of times during the material's outward journey? Every proposed mechanism had failed to match the observations, leaving a gap in understanding that could not be filled by incremental refinements to existing theory. The broader implications extended beyond this single object. If 3I Atlas represented a new class of interstellar visitor with properties not accounted for in current models, then future detections might reveal more objects with similar anomalies. The Vera Rubin Observatory, set to begin operations soon, would dramatically increase the detection rate of interstellar objects, potentially finding dozens or hundreds in the coming decade. If a significant fraction of these objects showed behaviors as puzzling as 3I Atlas, the field would face a sustained challenge to develop new frameworks capable of explaining an emerging population of poorly understood visitors from other stellar systems. The NASA image embargo and the delayed release of high-resolution data fed speculation about what might be hidden in observations not yet made public. While institutional caution and data quality concerns provided mundane explanations for these delays, the lack of transparency created an information vacuum that alternative theories rushed to fill. The scientific community's inability to provide definitive answers to straightforward questions about the object's size, composition, and jet mechanism made it harder to push back against speculation and maintain confidence that the mystery would eventually be solved through conventional scientific process. Resource allocation debates within the astronomical community reflected the tension between excitement about a unique object and frustration at the lack of clear results. Telescope time is always scarce, and the prioritization of 3I Atlas observations meant that other projects lost access to facilities. Some researchers questioned whether the investment was justified given the persistent ambiguities in the data and the failure to achieve observational breakthroughs despite substantial effort. Others argued that precisely because the object was so unusual, it deserved maximum attention, and that the difficulties only underscored the need for better instruments and more observation time. The unresolved nature of the 3I Atlas mystery left the field in an uncomfortable position. Here was an object that had been observed extensively by some of humanity's most advanced instruments, analysed by teams of expert researchers, and discussed in countless papers and presentations. Yet the core questions remained open. The straight jets could not be explained, the composition was anomalous, the size was uncertain, and the broader framework for understanding what 3I Atlas actually was, how it fit into the taxonomy of small bodies, and what it revealed about interstellar visitors remained contested and incomplete. The data was public, the observations were verified, but the explanation remained out of reach. Thermal modelling contradictions. Thermal models of cometary nuclei rely on well-established physics that has successfully predicted the behaviour of hundreds of solar system comets. These models calculate how sunlight heats the surface, how that heat conducts into the interior, and how temperature gradients drive the sublimation of ices at various depths. For 3I Atlas, multiple research groups applied these standard thermal models using the object's known orbital parameters, estimated size range, and observed activity levels. The results consistently failed to match what was actually observed, revealing yet another layer of physical inconsistency that defied conventional explanation. The basic framework of cometary thermal modelling starts with solar flux. As a comet approaches the Sun, the intensity of solar radiation increases according to the inverse square law. This energy heats the surface, raising temperatures until thermal radiation and sublimation cooling balance the incoming heat. The surface temperature determines which ices can sublimate. Water ice requires temperatures above roughly 200 Kelvin to sublimate at significant rates, while more volatile species like carbon monoxide can sublimate at temperatures as low as 25 Kelvin. By calculating the surface temperature as a function of distance from the Sun and local time of day on the rotating nucleus, models predict when and where sublimation should occur. For 3I Atlas at its perihelion distance, thermal models predicted surface temperatures in the range of 250 to 350 Kelvin on sunlit areas, depending on assumptions about surface albedo and thermal inertia. These temperatures were more than sufficient to drive vigorous water sublimation if water ice was present on the surface. The models predicted that water should have been the dominant volatile, with production rates orders of magnitude higher than what was actually observed. The spectroscopic measurements, showing only 4% water vapor in the coma, directly contradicted these thermal predictions. Researchers attempted to reconcile this discrepancy by modifying the thermal models. Perhaps the surface was covered by a thick dust mantle that insulated underlying ice, preventing water sublimation while allowing more volatile species to escape through cracks or pores. Mantle models had successfully explained low water activity in some solar system comets, but for 3I Atlas, the observed dust production rates were too high to be consistent with a thick insulating layer. The amount of dust being ejected implied that the surface was actively eroding, which should have exposed fresh ice and increased water production rather than suppressing it. Alternative thermal scenarios invoked compositional layering, with a volatile depleted outer shell overlying a more ice-rich interior. This structure might form if the object had experienced previous perihelion passages or prolonged exposure to interstellar radiation that had processed the surface layers. But the modelling showed that even with layering, the intense solar heating at perihelion should have driven enough heat into the subsurface to trigger water sublimation at depth. The thermal wave from surface heating penetrates several meters into cometary nuclei during close solar approach, reaching layers that should contain pristine ices if the object had a typical cometary composition. The thermal models also predicted specific patterns in the diurnal variation of activity. As the nucleus rotates, different areas cycle between day and night. Models predict that sublimation should peak shortly after local noon on each surface element, then decline as that area rotates into shadow and cools. This diurnal cycle should produce brightness variations in the coma that lag behind the solar illumination pattern by an amount determined by the surface's thermal inertia. Observations of 3I Atlas showed brightness variations consistent with the rotation period. But the detailed phase relationships between rotation and brightness did not match thermal model predictions. The activity seemed less strongly tied to local solar illumination than expected, suggesting that either the thermal response was very different from typical comets, or that the activity was driven by processes not directly tied to solar heating. Some teams explored cryovolcanic models, where subsurface pressure from trapped volatiles could drive eruptions independent of surface temperature. Cryovolcanism has been observed on some icy moons in the outer solar system, where tidal heating or residual internal heat drives the explosive release of volatiles through surface fractures. For a small cometary nucleus without internal heat sources or tidal forcing, cryovolcanic activity would require a different mechanism, perhaps pressure buildup from volatile sublimation at depth, creating pathways to the surface. These models could potentially explain activity patterns decoupled from local solar heating. but they introduced new problems. The pressure required to drive jets over million-kilometer distances vastly exceeded what could be generated by reasonable sublimation rates in a small, porous nucleus. The energy budget did not close. The mismatch between thermal predictions and observed behavior extended to the jets themselves. Thermal models predict that jets should originate from the warmest areas on the nucleus, typically near the subsolar point where solar heating is strongest. The images of 3I, Atlas, showed jets extending in multiple directions, not all consistent with originating from the hottest surface regions. Some jets appeared to emerge from areas that should have been relatively cool based on their orientation relative to the Sun. This spatial distribution of jet sources contradicted the expected correlation between temperature and activity. Energy balance calculations added another constraint. The total energy available from solar heating could be calculated precisely from the known distance and the estimated surface area. This energy had to account for reflected sunlight, thermal radiation from the warm surface, and the latent heat of sublimation for all the volatiles being released. When researchers added up the observed mass loss rates for dust and gas, converted these to energy requirements for sublimation and acceleration, and compared to the available solar energy, the numbers were tight. There was barely enough energy to drive the observed activity if the process was reasonably efficient. Any mechanism that involved additional energy sinks, such as ionization or electromagnetic acceleration of material, would exceed the available energy budget unless some unseen energy source was present. The thermal modeling failures were particularly frustrating because thermal physics is generally well understood and the models have been extensively validated against laboratory experiments and spacecraft observations of solar system comets. The fact that these reliable tools could not reproduce the behavior of 3I, Atlas, suggested either that the object's physical properties were extreme outliers, far beyond the range tested by previous cometry studies, or that assumptions fundamental to thermal modeling, such as the dominance of solar heating as the energy source, did not apply. Neither possibility was comforting. Both implied that 3I, Atlas, was operating under conditions or by mechanisms that existing frameworks were not equipped to handle. Magnetic field implications. Magnetic fields in cometry environments are typically weak, chaotic, and generated through the interaction between the solar wind and the ionized coma rather than by the nucleus itself. Comets are not expected to have intrinsic magnetic fields. They lack the molten metallic cores or active dynamos that generate planetary magnetic fields. Yet the straight jet phenomenon observed in 3I, Atlas, prompted several research groups to investigate whether magnetic fields might play an unexpected role in collimating or guiding the outflowing material. The physics of plasma in magnetic fields is well established, and if fields of sufficient strength and organization existed around the nucleus, they could potentially influence the trajectories of ionized gas and charged dust particles. The solar wind carries with it the Sun's magnetic field, stretched into a spiral pattern by the Sun's rotation as it flows outward through the solar system. When this field encounters a comet, it drapes around the obstacle, creating a region where the magnetic field lines are compressed and distorted. This draped field configuration has been measured by spacecraft visiting several solar system comets, and the structure is reasonably well understood. The field strength in the inner coma, close to the nucleus, can reach tens of nanotesla, orders of magnitude stronger than the undisturbed interplanetary field, but still weak compared to planetary magnetic fields. For magnetic fields to collimate jets over million-kilometer distances, they would need to be significantly stronger and more organized than the typical draped field structure. The Lorentz force, which acts on charged particles moving through a magnetic field, scales with the product of the particle's charge, velocity, and the field strength. For this force to dominate over the outward pressure of the expanding gas and overcome the random thermal motions that spread material in all directions, the field would need to be both strong enough to exert significant force and organized into a geometry that channels material along specific directions rather than deflecting it randomly. Plasma physicists at several institutions calculated the field strengths and configurations that would be required to explain the jet collimation. Their models assumed that some fraction of the outflowing gas was ionized, creating a population of charged particles that could respond to magnetic forces. They tested various field geometries, including dipolar fields centered on the nucleus, helical fields twisted by rotation, and current sheets where magnetic field direction reversed sharply. The calculations showed that field strengths of at least several hundred nanotesla, sustained over distances of thousands of kilometers from the nucleus, would be necessary to significantly affect particle trajectories. No direct measurements of the magnetic field around 3I Atlas existed. No spacecraft had passed close enough to the nucleus to make in situ field measurements, and remote sensing of magnetic fields in cometary Comet is extremely difficult. Indirect constraints came from observations of the comet's structure and behavior. If very strong magnetic fields were present, they should affect the motion of solar wind particles and create observable features in the plasma tail or the hydrogen envelope. The MAVEN ultraviolet observations and the optical images of the plasma tail showed no obvious signatures of unusually strong or organized magnetic fields. The tail appeared to follow the expected anti-solar direction, bent and shaped by the solar wind in ways consistent with typical field strengths. Some researchers proposed that the nucleus itself might generate a magnetic field through some unconventional mechanism. Certain types of rock, particularly those containing iron-rich minerals, can carry remnant magnetization if they formed in the presence of a strong field and were later cooled. Meteorites from differentiated asteroids sometimes show remnant fields, evidence of ancient magnetic activity in their parent bodies. If 3I, Atlas's nucleus, contained magnetized material, it might generate a weak dipolar field, but the field strength from remnant magnetization in a small body would be extremely weak, likely only a few nanotesla at the surface and declining rapidly with distance. This was far below what would be needed to collimate jets. More exotic proposals invoked currents flowing within the nucleus or through the coma. Electric currents generate magnetic fields, and if sufficient current could be driven through the conducting plasma of the coma, it might create field structures strong enough to affect material flow. The challenge was identifying a plausible mechanism for driving such currents. In planetary magnetospheres, currents are generated by the motion of plasma across field lines, by charge separation in the ionosphere, or by electromagnetic induction in conducting layers. Cometary nuclei lack the scale and the internal structure to support these mechanisms. Without a clear energy source and a conducting pathway, the currents needed to generate collimating fields could not be sustained. The investigation of magnetic field effects also considered the role of dust grains. Dust particles can acquire electric charge through UV photoelectron emission, where solar ultraviolet radiation knocks electrons off the grain's surface, leaving it positively charged. Charged dust grains respond to electric and magnetic fields through the same Lorentz force that affects ions and electrons. If the dust in 3I, Atlas's jets, was substantially charged, and if magnetic fields were present, the dust trajectories might be shaped by electromagnetic forces in addition to gas, drag, and radiation pressure. This could potentially explain some aspects of jet collimation, Laboratory experiments on dusty plasmas have shown that charged dust can organize into complex structures, sometimes forming strings or filaments aligned with magnetic field directions. These structures form when electrostatic and magnetic forces balance against thermal motions and drag forces in ways that create stable configurations. Extrapolating from laboratory conditions to the scale of a cometary coma requires enormous leaps, and most plasma physicists remain skeptical that similar structures could form or persist in the low-density, turbulent environment around an active comet. The physics was interesting but speculative, and no observational evidence directly supported the presence of organized dust structures at 3I Atlas. The magnetic field hypothesis remained in the category of interesting but unproven ideas. The lack of direct field measurements meant that strong claims about field strength and geometry were necessarily speculative. The absence of obvious observational signatures of unusual magnetic activity argued against extremely strong or highly organized fields. Yet the possibility could not be completely ruled out, and the topic remained an active area of theoretical investigation. If future missions could deploy magnetometers near interstellar objects, direct field measurements might either vindicate magnetic collimation models or finally put them to rest, narrowing the range of possible explanations for phenomena like the straitjets of 3I Atlas, dust grain dynamics. Understanding the motion of dust grains in cometary comae requires accounting for multiple forces acting simultaneously on particles ranging from submicron to millimeter scales. For typical solar system comets, the dominant forces are well characterized. Gas drag from the sublimating volatiles accelerates grains away from the nucleus. Solar radiation pressure pushes them in the anti-solar direction, and the weak gravitational field of the nucleus exerts a small, attractive force. The balance among these forces determines the trajectories of grains, which in turn determines the shape and brightness of the dust coma and tail. For 3I Atlas, standard dust dynamics models failed to reproduce the observed jet structures, suggesting that either the dust properties or the forces acting on the grains were unusual. Gas drag is typically the dominant force launching dust from the surface. As ice sublimates, the expanding gas carries entrained dust particles outward. The effectiveness of gas drag depends on the particle size and the gas density. Small particles, with high surface area to mass ratios, couple strongly to the gas and are accelerated to velocities approaching the gas expansion speed. Larger particles couple more weakly and move more slowly, creating a size-dependent velocity distribution. Observations of 3I Atlas showed dust grains reaching velocities around 400 meters per second, consistent with typical cometary gas speeds, and suggesting that, at least for some size range, the coupling between gas and dust was operating normally. Radiation pressure from sunlight affects dust grains based on their size and optical properties. For particles smaller than about 1 micron, radiation pressure can exceed the gravitational attraction to the nucleus, pushing them away in the anti-solar direction and eventually sweeping them into the dust tail. Larger particles are less affected by radiation pressure relative to their mass and follow trajectories more strongly influenced by their initial velocity from gas drag. The size distribution of dust particles determines the overall appearance of the coma and tail, with smaller particles contributing to a broad, diffuse tail and larger particles remaining closer to the nucleus or forming narrower structures. For 3I Atlas, detailed analysis of the coma brightness and color provided constraints on the dust size distribution. Observations at multiple wavelengths allowed researchers to infer the typical particle sizes contributing most to the scattered light. The results indicated a size distribution not dramatically different from typical solar system comets, with particles ranging from submicron to hundreds of microns in radius. This suggested that the dust production mechanism was not wildly anomalous in terms of the particle sizes it generated. Yet the straight jets implied that these particles were following trajectories that simple radiation pressure and gas drag models did not predict. One hypothesis involved electrostatic forces. Dust grains exposed to solar ultraviolet radiation can acquire substantial electric charges, and if electric fields existed in the coma, charged grains would experience forces in addition to gas, drag, and radiation pressure. The magnitude of the electrostatic force depends on the grain's charge and the strength of the electric field. Calculations showed that for typical cometary conditions, the charge on dust grains would be small, a few hundred to a few thousand electron charges for micron-sized particles. Without strong electric fields, the electrostatic force would be negligible compared to radiation pressure and gas drag. But if electric fields in the coma were much stronger than typical, perhaps due to charge separation from intense ionization or unusual plasma conditions, then electrostatic forces could become significant. Some plasma models of cometary comae predict the formation of electric field structures, particularly near boundaries between the neutral coma and the ionized plasma surrounding it. If 3I, Atlas, had such structures, and if they were stronger or more organized than in typical comets, charged dust might be accelerated or deflected in ways that kept it aligned along specific directions. This remained speculative, requiring both stronger fields and higher dust charges than typically observed. Dust grain rotation and alignment added another layer of complexity. Non-spherical dust particles can be spun up by radiation pressure or by collisions with gas molecules. Once rotating, grains can align with magnetic or electric fields through various torque mechanisms, potentially creating populations of dust with preferred orientations. If dust grains in the jets of 3I, Atlas, were substantially aligned, they might scatter light differently than randomly oriented grains, potentially affecting the observed brightness and appearance of the jets. Observations of polarized light from the comet could test this hypothesis, as aligned grains produce different polarization signatures than random distributions. Some research groups conducted polarimetry observations of 3I, Atlas, measuring the degree and direction of linear polarization in the scattered sunlight. The results showed polarization levels broadly consistent with typical cometary dust, without obvious signatures of unusual grain alignment or exotic scattering properties. This did not rule out alignment effects entirely, but it suggested that if alignment was occurring, it was not producing dramatic observable signatures at the sensitivity levels achieved by the observations. More detailed polarimetric studies across multiple wavelengths and observation geometries might reveal subtler alignment effects. The dust production rate itself presented another puzzle. Estimates based on the coma brightness and models of dust scattering gave mass loss rates in the range of hundreds to thousands of kilograms per second during the peak activity near perihelion. For a nucleus only a few kilometers across, sustaining this production rate for weeks required a substantial reservoir of dust and a mechanism for continuously exposing fresh material. If the nucleus was porous or fragile, surface layers might erode quickly under solar heating and gas pressure, maintaining high dust production. But if the nucleus was more cohesive or ice-poor, sustaining high dust rates would be difficult without fragmenting or rapidly depleting the surface. Fragmentation remained a possibility that could not be definitively ruled out. If the nucleus had split into several pieces near perihelion, each fragment could produce its own dust stream. and the combination might create the observed brightness and spatial distribution. The lack of confirmed observations of multiple distinct nuclei argued against major fragmentation, but subtle splitting into a few closely spaced fragments could be difficult to detect in unresolved images. Some researchers continued to advocate for the fragmentation hypothesis as a way to explain both the high dust production and some of the unusual jet geometries, while others maintained that the light curve data and spectroscopic observations were more consistent with an intact nucleus. The dust grain dynamics of 3I Atlas illustrated how multiple physical processes interact in complex ways to determine observable features. Standard models captured much of the basic behavior, explaining the presence of a coma and tail and predicting reasonable dust velocities and size distributions. But the details, particularly the straightjet morphology and the sustained high dust production, pushed beyond what standard models could comfortably accommodate. Whether the explanation lay in unusual dust properties, unaccounted forces, or geometry and projection effects remained unresolved, contributing to the broader picture of an object that consistently defied straightforward interpretation: orbital evolution constraints. The trajectory of 3I Atlas through the solar system carries information about where the object came from, how long it has been travelling through interstellar space, and what forces have affected its path. Precise orbital determination requires numerous observations spanning weeks to months, tracking the object's position against the background stars and measuring its velocity through Doppler shifts in spectral lines. For 3I Atlas, extensive astrometric observations from ground-based telescopes and positional measurements from spacecraft images provided a high-quality orbital solution that revealed intriguing constraints on the object's history. The orbital eccentricity of 3I Atlas was measured to be greater than 1, confirming its hyperbolic trajectory and interstellar origin. Objects gravitationally bound to the Sun follow elliptical orbits with eccentricity less than 1, while unbound visitors, on their first and only passage through the solar system, travel hyperbolic paths with eccentricity exceeding 1. The hyperbolic excess velocity, the speed the object possessed relative to the Sun when infinitely far away, was calculated to be above 23 kilometers per second. This value could be compared to the velocities of nearby stars to constrain which stellar neighborhood 3I Atlas might have originated from. Tracing the trajectory backward in time revealed the object's entry vector into the solar system. The incoming direction pointed toward a region of the sky consistent with the general direction of the solar system's motion through the local interstellar medium, but not precisely aligned with any specific nearby star. Detailed orbit integrations that accounted for planetary gravitational perturbations showed that the trajectory was slightly deflected by the gravity of Jupiter and the other giant planets, but these deflections were small and did not dramatically change the object's path through the inner solar system. Researchers attempted to identify a stellar source by extrapolating the trajectory backward millions of years, accounting for the Sun's motion relative to nearby stars and the typical velocities of stars in the galactic neighborhood. This exercise was complicated by uncertainties in both the object's trajectory and the motions of potential source stars. After accounting for realistic error bars, the analysis identified several candidate stars that 3I Atlas might have passed close to within the last few million years, but none stood out as a definitive source. The most likely scenario was that the object had been travelling through the galaxy for a very long time, with its current trajectory shaped by many gravitational interactions over its history, rather than by a recent ejection from a specific stellar system. The orbital solution also constrained how much non-gravitational force had affected the trajectory. Non-gravitational forces in comets typically arise from outgassing, where the asymmetric ejection of material creates a rocket effect that changes the object's velocity. For typical comets, this effect can substantially alter the orbit over multiple apparitions, creating measurable deviations from purely gravitational trajectories. For 3I, Atlas, the astrometric data allowed researchers to test whether non-gravitational forces were present and, if so, to estimate their magnitude and direction. The analysis showed evidence for small non-gravitational accelerations, consistent with what would be expected from a comet with vigorous outgassing. The magnitude of the effect was comparable to that seen in active solar system comets of similar size and activity level. However, the direction of the non-gravitational force was harder to constrain. Depending on which jets were most active and how the thrust from outgassing was distributed around the nucleus, the net force could point in various directions. The data did not have sufficient precision to uniquely determine the thrust direction, leaving some ambiguity in the orbital solution. One interesting consequence of the non-gravitational forces was their potential effect on the rotation state. Outgassing from an irregular nucleus can create torques that change the rotation period and axis orientation over time. For 3I, Atlas, the measured rotation period of 16.16 hours was a snapshot from a specific time. If strong outgassing torques were acting, the rotation period might have been different weeks or months earlier, and it might change in the future. The light curve observations showed no clear evidence of rapid spin changes during the monitoring period, suggesting that any torques were relatively small, or that they happened to be oriented in ways that did not produce large spin-up or spin-down effects during the observed interval. The stability of the orbit and rotation against fragmentation forces was another consideration. As the nucleus heated during a close solar approach, thermal stresses from uneven heating could create fractures or cause the object to split apart. The tensile strength of cometary material is low, and objects held together only by weak self-gravity can disintegrate if rotation or thermal stress exceeds the material's ability to resist. The rotation period of 16 hours was well below the threshold where centrifugal forces alone would tear apart a cohesive body several kilometers across. But if the nucleus was already fractured or weakly bound, additional stresses from outgassing or thermal expansion could have triggered breakup. The absence of confirmed fragmentation during the observed perihelion passage set lower limits on the nucleus's tensile strength and structural cohesion. These limits could be compared to values measured for samples of cometary material returned by missions like Stardust or studied in laboratory analogues. The results suggested that 3I, Atlas, was at least as cohesive as typical cometary nuclei, able to withstand the stresses of close solar approach without breaking apart. This constraint was useful for modelling the internal structure and composition, ruling out scenarios where the nucleus was an extremely fragile rubble pile or a loosely bound aggregate that would have disintegrated under the observed conditions. The long-term orbital evolution beyond the current solar system passage could also be calculated. After rounding the Sun and heading back toward interstellar space, 3I, Atlas, would gradually climb out of the Sun's gravitational well, its speed declining as gravitational potential energy converted back into kinetic energy in the opposite sense from the inbound journey. Eventually, at vast distances, the object would reach its asymptotic velocity and continue travelling through the galaxy along a new trajectory shaped by its encounter with the solar system. The encounter had changed the object's velocity by a few kilometers per second, a small but measurable effect that would shift its future path through the galaxy and potentially alter which stars it might encounter in the distant future. Observational bias analysis. The detection and characterization of interstellar objects is subject to numerous observational biases that affect which objects are found, when they are discovered, and how well they can be studied. Understanding these biases is critical for interpreting what 3I Atlas represents, and for assessing whether it is truly anomalous or simply the first well-observed example of a common but previously undetected class of interstellar visitor. The biases operate at multiple levels, from the fundamental sensitivity limits of survey telescopes to the human and institutional factors that determine how observations are conducted and analysed. Brightness is the most fundamental observational bias. Survey telescopes detect objects based on how much light they reflect or emit, and fainter objects are systematically missed. For interstellar objects moving through the inner solar system, brightness depends on size, surface reflectivity, distance from both the Sun and Earth, and activity level. Small, dark objects, or those that pass through the solar system at large distances, remain below detection thresholds and are never discovered. The 3 confirmed interstellar objects detected so far, Oumuamua, Borisov, and 3I Atlas, were all bright enough to be detected, but this says nothing about the potentially much larger population of fainter objects that went unnoticed. The detection rate is also strongly affected by the sky coverage and cadence of surveys. Most astronomical surveys scan the sky repeatedly, looking for objects that move or change brightness between observations. The time interval between repeat observations determines which objects are detected. Fast-moving interstellar objects on highly inclined orbits can traverse large distances in a short time, and if the survey cadence is too slow, they might be present in one observation but have moved out of the field of view before the next observation. This temporal bias means that objects on certain types of trajectories are more likely to be detected than others. For 3I Atlas, the detection occurred during a period when multiple survey programs were operating and when the object happened to be both relatively bright and in a favourable position in the sky. If the same object had passed through the solar system a decade earlier, before some of these surveys started, it might never have been discovered. The historical record of comet and asteroid discoveries shows a strong time dependence, with detection rates increasing as survey capabilities improved. Extrapolating backward to estimate how many interstellar objects might have been missed in past decades is highly uncertain, but suggests that several could have passed unnoticed. The follow-up observation bias is equally important. Once an object is detected, securing additional observations to refine its orbit, measure its physical properties, and monitor its activity requires telescope, time, and coordinated effort. Bright, unusual objects attract more attention and are allocated more resources than faint, ordinary-looking ones. 3I Atlas, with its early identification as a potential interstellar visitor and its subsequent display of vigorous cometary activity, received extensive follow-up. An object with less dramatic features might have been observed only sporadically, leaving gaps in coverage that would prevent detailed characterization. The geometric bias related to orbital inclination played a significant role for 3I Atlas. Objects on retrograde orbits spend less time within the inner solar system and pass through at higher relative velocities compared to prograde objects. This makes them harder to detect and track. The near-ecliptic alignment of 3I Atlas partially offset this difficulty by keeping the object close to the plane where most survey effort is concentrated. But the retrograde motion still meant that the window for detailed observations was compressed compared to what it would have been for a prograde object on a similar orbit. Solar conjunction timing created another layer of bias. Objects that pass close to the Sun from Earth's perspective are unobservable for periods of days to weeks due to the sun's overwhelming brightness and the danger of pointing telescopes too close to the solar disk. 3I Atlas reached perihelion just days after solar conjunction, meaning that its brightest and most active phase occurred when it was difficult or impossible to observe from most ground-based facilities. This timing was unfortunate for observational coverage, but also highlighted how geometric factors can hide objects during critical phases of their passage. Spacecraft observations partially mitigated some ground-based biases, but introduced their own limitations. Instruments on Mars' orbit or stationed at other vantage points in the solar system could observe 3I Atlas during periods when it was invisible from Earth, filling gaps in coverage. However, spacecraft observations are constrained by pointing restrictions, data rate limitations, and competing priorities for limited instrument time. The Mars Reconnaissance Orbiter's observations of 3I Atlas required careful planning to balance comet observations against the spacecraft's primary mission of studying Mars, and the allocated observation time was necessarily limited. The wavelength bias affected what physical properties could be measured. Most surveys operate in visible or near-infrared wavelengths, where reflected sunlight dominates. This biases detections toward objects with relatively high albedo or active Comet that scatter light efficiently. Objects that are dark and inactive, or that emit primarily at wavelengths outside the survey bandpasses, are systematically underrepresented in detection statistics. For 3I Atlas, the strong activity made it relatively easy to detect and study, but this means it might not be representative of the broader population of interstellar objects, which could include many inactive bodies. Publication bias operates at the level of scientific literature. Unusual, dramatic, or puzzling objects generate more papers, conference presentations, and public attention than ordinary objects with well-understood properties. This creates a feedback loop where anomalous objects receive disproportionate study, potentially leading to the impression that they are more common than they actually are. For 3I Atlas, the straight jets and other unusual features ensured extensive coverage in both professional and popular outlets, but this attention might overstate how representative the object is of typical interstellar visitors. Quantifying these biases to estimate the true population of interstellar objects requires careful statistical modeling. Researchers use simulations to generate synthetic populations of objects with various size distributions, trajectory distributions, and activity levels. Then run these populations through models of survey detection to see what fraction would be found. By comparing the simulated detections to actual observations, they can estimate correction factors that account for the biases and infer properties of the underlying population. Current estimates suggest that the solar system is regularly visited by interstellar objects, with perhaps one detectable object per year passing through the inner solar system, but uncertainties in the bias corrections make these estimates uncertain by factors of several. For 3I Atlas specifically, the question of representativeness remains open. Is it an unusual outlier, a rare object whose properties placed it at the extreme end of the distribution? Or is it simply the first member of a common class to be well observed, with many similar objects having passed undetected or unrecognized in the past? The biases that affect detection and characterization make this question difficult to answer definitively. Only with larger samples from future surveys will the position of 3I Atlas in the broader population become clear, revealing whether its puzzling features are unique or common among interstellar visitors.